Hello, everyone. Um, we're going to talk about chapter 16, energy resources. This is the last chapter before the midterm exam. So midterm will be next week. And I'm going to post the exam questions, I think, on Thursday. And then you have a week, any time of the week you can choose to do that. I think please review the materials first. Then before doing that, I gave everyone one chance to do this. Okay. So, but if anything happened, if you have specific accommodation requests, please let me know, and I can make a special arrangement for you. So this is energy resources in this chapter. So here it's a picture of a drilling machine. So it's drill a big hole under this on the ground. Then here's the drilling mud, pretty nasty, and could be contaminated. Can contaminate. Here is like they have a waterproof pool, so make sure those drilling bloods no going nowhere to protect the environment. Otherwise, it's it's a lot of chemicals. Okay, so in this chapter, we're gonna understand the concept of peak oil and how it might impact our economic and social environment, and know the several patterns of energy consumption in the United States, and know the type of major fossil fuels and environmental impact associated with their development, understand nuclear energy and associated important environmental issues, understand geothermal energy, how it is produced, and its future as an energy resource, and know the main types of alternative and renewable energy and their environmental significance, and know the important issues related to energy policy, particularly the concept of sustainable energy development. So, so as we know that energy is very important. It's the fundamental lifeblood for industrialization, for especially for the United States, it's highly technical society, and we consume a disproportionately amount of energy resources, which means that we have like about only 5% of the world's population, but the United States consumes probably 20% of the world's total energy. Now, the question is that how we're going to face this growing challenge, how we can break energy dependency, and also sustain a development and high standard of living. And we have been constantly worried about from past to present and maybe in the future over the prices, the dependency, and the power failure and so forth. And hopefully this chapter will help you to understand some of the important concepts. So first, it's a case study. So here's, we're going to look at the history of energy transition starting 1800 to the present. So here's the figure. So as you can see that from 1800, the starting point is that the energy resources are wood. So about 1850, there's a peak. So wood peak. And then start 1850, we're going to coal, consuming coal. And then at about 1900, we start to use oil. And then about 2030, and start to use natural gas. And after 1950s, we start having alternative energy, including nuclear energy, hydro power, wind, and solar energy, and so forth. So here is sort of the history. So wood consumption starting 1800, but it probably takes about 100 years for us to try to transition from wood to fossil fuel. Okay, so here's a fossil fuel and start fossil fuel, which is a coal in 1850, and take about 9 to 20s, something like that. So this transition from 1850 to 1950, and that's probably take about 100 years for the full transition. By the time 1950, the wood consumption is actually renewed down, and now, although there are biofuels, and people these days start to use some of the use that as alternative energy, come back to using wood. There's a shortage. The event triggers the transition is actually the shortage of wood in 1812 in Philadelphia led to the experiments of burning coal, and the first oil was complete in 1858, and then after that time, the primary source of oil was actually whale oil, and following the use of petroleum that produced kerosene, and the United States left the whale hunting industry behind. So in the beginning, people, these days, people continue hunting whale, and one of the big reasons is that whale oil can be used as energy resources. And later we'll try to explain what is peak oil production. So peak oil basically means that when half of Earth's recovery oil will have been produced and used, and which likely happened between 2020 to 2050. So exactly what happened is still, depend on many factors, including technological factor, our recovering techniques, and also consumption, the speed of consumption, and so forth. But in some is that the amount of fossil fuel in the Earth is finite. So once one kind of resource is being used up, we have to transition from one to the other. Typically, during the transition, the fuel will be less reliable to something very reliable, very less dense, produce less amount of energy, like wood per kilograms, and to something is more concentrated form. So, so basically, this is the deal. And in the future, maybe we're going to change to alternative energy, to nuclear energy, solar energy. Because back again, it's coming to actually diffusive energy. How we can concentrate on this diffusive energy. So this kind of turning solar energy into useful energy at low cost has now been achieved. Take a lot of technological development. But however, in the future, this from wood transition, what we learn to fossil fuel, and in the future maybe to alternative energy, it's really not the technological. We actually have the technology to do this transition. Our problem is people's willingness, the willpower, how people determined to make this transition. So if we look back to the history, energy shock, past and present, about 2,000 years ago, the ancient Romans, they actually using wood at that long time, even before 1800. So the Romans using wood, they actually had central heating, consume a large amounts of wood, and sometimes they said, 125 kilograms per hour, and then very quickly they used up the wood resources around the Romans Empire, and then they have to import wood from distance, so it's far away, from about 1,000 miles, 1,600 kilometers away, and this can also be used up. So they at the end they actually start to use solar energy as alternative, and they are so efficient in using the solar energy, and sometimes they actually establish laws and to protect people's right to use the solar energies. For example, extreme case that when someone build a house, then they cannot, it's illegal to construct building that shade the other buildings. and next door. So they have to give the neighbors enough sunlight. So in the summer of 2008, and also a few years ago, the U.S. was shocked by the rapid price increase in gasoline. And it's actually sort of a long story. Before 2008, the gas price was quite low. It was at like $40 a barrel. Basically, that's the unit. A barrel is about 42 gallons, something like that. By the time 2008, it actually reached about $100 per barrel, the crude oil. So that's nearly doubled. So this is a huge change from 40 in 2009. And then these days, like 72 something. So at certain points at 42. So the gas prices were very low. When I was a student, I experienced that the gasoline price was actually below $1. That was pretty low. Now it's $2, $3, $3. It's normal. And the crude oil is like $70 per barrel ish. And in 2008, it increased to $100 per barrel. So people faced inflation, all kinds of things can happen. And before then, it was actually has the California energy crisis, and which is rolling blackouts. And this is actually before this energy shock, 2008 happened in 2008. It was because there's so in California, because of the population increases, so the utility company also has been deregulated years before then, before 2008. And so the California needs a lot of energy because there's prosperous people migrate there, and a lot of people living there. So and California does not have a lot of energy these days. Energy in California is quite expensive. At the time, there's scandals. Then some of the traders in the utility company was asked like 900 times increase, 9 times of their market price. And then the California energy was skyrocketing. And then it was being investigated, and it was turned out to be a scandal. And then so energy crisis is not a new topic. It's occurred in historic times, but I think energy crisis, as population increases and the standard of living increases, and also most important things that there's a finite amount of resources. The amount of fossil fuel on Earth is finite. Therefore, eventually, energy crisis is going to happen. It's going to come back again and again and again. So we have to find a way to, as we said in the beginning, so bigger question is that how we can break energy dependence and sustain development and high standard of living. Right. So the first question is that the peak oil. So we benefit from fossil fuels, and especially oil, and this is sort of undeniable. Of civilization, the fast breakthrough in technology and everything is actually depend on energy, which is in the last 30, 40 years is due to the oil. The problem associated with oil also is unquestionable. We know there's a lot of problems. So here's a chart from the 1950s to 2010, and these are millions of barrels per day. This is the net imports. So we import lots of oil from all over the world. And then also in the United States, the production was actually gear up. Then the consumption before 2010 is always very high. So we have to produce, and also that imports to meet our consumption. So consumption is always higher than what we produce. Therefore, we have to import lots of gasoline. This is up to 2010. Later on, I'll show you some new data. Okay, so so here is the concept, which is the comparison of the discovery, which is the exploration. We discovered all oil, then since 1800 we start to know and find oil, and then and people start to more and more oil being discovered about 1960s. That's a peak of exploration, and discovered the maximum amount of oil. Then after that it decreases, okay, because there's always a limited amount of oil. And this is consumption. Consumption's increase. 1960s, the amount of oil we discovered is about 4 or 5 times, 4.8 times of what we the oil we discovered is about 4 to 8 times of what we'll consume. But by the time 1980s, that's about equal in the 1980s, equal amount of discovered and consumed. By the time of 2020 or 2000, the amount of what we consume is much higher. It's about 3 times higher than what we discovered. So this means that, again, it's just saying that the oil is non-renewable, and these days it's consumed very, very fast. And then, but the amount of oil we discovered is actually reducing. Therefore, the consequences is the growing demands and can cause water pollution, air pollution, global warming, and also lots of global economic and political instabilities. Okay. So then there's a concept, which is the peak oil. Peak oil is the time when half the Earth's oil extracted and used. So, so here is the oil production. So this is the production, and then demand. If we see that production is following the demand, and by the time it reached the peak oil, which is half of what is consumed, after that, the production can decrease. Okay, if you're thinking about this as a symmetric curve, so this side and this side should have the same area. Therefore, this is half. Okay, thinking about a symmetric curve. Perfect. And after that, the demand will probably going to increase, even if it stay the same, then because the decrease in production without gap. So therefore, demand is more than production, then they drive the oil price. Okay, it get more and more expensive. Now here it shows that if we continue, so here same thing, this is world oil. So this is the again, there's a production, then there's a consumption here. And then if the consumption is the same, and then we can turn a corner, then we'll see that peak oil happens somewhere here, which is the flat peak oils between 2008, 2025. Then after that, we're going to decrease. Then that's the flat peak oil. That's one scenario. If we consume 35 billion barrels per year, then we'll reach the peak. We reduce that amount. We reach the peak about 2015. Okay. So then if we have a different scenario, we actually have different, the rule of thumb is that if we consume less, the peak time will be delayed. And then the demand will be always have it follows the production, but always the gap. Demand is more than what we produce. Then we have lots of different kind of problems. Okay. So right now, so here it shows the energy produced using all kinds of energy. This is the petroleum, natural gas, and coal, and this is the biomass, hydroelectric power, nuclear power, and so forth. So you can see that these days, in the 2000, by the time 2010, about 90% of US energy consumption is actually coming from fossil fuels. So that's include natural gas, coal, and petroleum. That together, that's about 90% of that. And then after that, there's about 10% hydropower and about 10% of nuclear electric power. And you can see that fossil fuel actually increases to the peak of 1980s-ish. And then they actually decreased a little bit, 1976, that's the peak. Then decreased, then it continued to increase about 2005, they started to decrease. Okay, so fossil fuel, again, is non-renewable, and the fossil fuel peak discovery in 1960s, we look at that, we know that. And then the consumption increasing over time, the rate of increase, but variable, the peak increase during 1950s to 1974, and after that, it exactly goes down and continues to increase a little bit. Okay, so so this is this is, and also you look at the percentage, and here is using exajoules, and which is 10 to 18s later. No, exajoule, joule. So this is the energy normally we talk about. Okay, so if you look at this, it's 35% petroleum, natural gas 33%, coal 20%. So add together is 78%, almost. It's 43, 78% of energy. 35, 23, 20. This is exajoule percentage. Sorry about that. And this nuclear energy is 8, and biomass is 4, exajoule, and the hydroelectric power 3, geothermal solar is only 1%, or 1-ish. So this is how they're distributed. Here I want to show the petroleum imports total from different places, from OPEC, the Persian Gulf, and Canada. So here is the total petroleum imports. So that production. So we can see that the imports increases, total imports, and then 2005 has actually reached the maximum, the million barrel per day. Then it actually decreases. In the beginning, in the 1960s to 2010, majority of the imports coming from OPEC countries. And then Persian Gulf has a peak in 1976, and also here, and 1976 is also maximum use of fossil fuels, peak there, and then decreases. And then Canada, say tar sand, all kinds of oil actually steadily increase. Okay. Here is the petroleum consumption, production, imports, exports, and net imports from 1950 to 2022. As you can see that United States, here again, this is the consumption to 20 million barrels per day. It's the peaked at 1976. So after that, it's actually a decrease, then it peaked about 20. It's pretty steady. And normally we need about 20 million barrels per day of petroleum. And the production is here. So production is actually increased. So in the beginning, it was like almost half of them can be produced here. Then later, starting 2006, drilling, offshore drilling, and the United States, the production of the fossil fuel increases. By the time 2020, the first time, the production and consumption is equal, which means that the total imports is here, is the net imports is here, is actually reduced to zero about 2020. It's the first time we actually do not rely on imports from other countries. Although you can see that imports still increase, but also has exports. So not only we import, we export. The import and export is the same. So it's about 2020. This is like us. We don't depend on like OPEC countries or we import some of the petroleum and exports the other because the quality of the petroleum could be different. All right, some energy terms, and later you will see that we're gonna discuss type of energy: the light, electrical energy, chemical, thermal, mechanical, and nuclear. So basically, it can be divided into two kinds. One's called kinetic energy. Kinetic energy is the movement of something. Like light is movement of photon. Electrical energy is movement of electrons. Chemical energy, thermal energy is the vibration. Mechanical energy and nuclear energy, reactivity. Chemical energy is actually a potential energy which stored in organic matter, for example, or fossil fuels. Okay, so those are potential energy. When it's burned, it will turn into heat, turn into thermal energy. Some energy unit, and what's energy is the capacity to do work. Normally we use joules. Joules is 1 Newton force applied over a 1 meter. So it's the force times meter. So normally when we talk about global energy, we use exajoule, which is 10 to 18th joule. So that's more, it's the gigajoule is GJ, 10 to 9. And then it's the it's a 12 is a billion joules, and then exajoules is 10 to 18th, and also quadjoules. A quad, basically it's 10 to 1.055 exajoules. And also when we talk about power, we use the rate of energy transfer are used is watt. So it's 1 watt is 1 joule per second, and the megawatts is 1,000 kilowatts or 10 to 6 watts. There's a million watts. Terawatts is 10 to 12 watts. I'm going to talk about a lot of those terms. All right. So energy policies, basically every country in the future, we have to establish some kind of energy policies to promote conventional energy resources. We're going to encourage alternative energy, provide for energy infrastructure, promote conservation measures, seriously consider nuclear power, and promote research. These are the general policies in every country that gonna do in the next foreseeable future. So before we talk about energy, and I want to talk about the balance. Okay, so energy cycles, and I talked about this in my Earth System Science, and try to give you a picture. So if we think about Earth as a system, and we look at energy in and energy out, the budget, and this energy in and out, we talk about life zone. We talk about the surface of the Earth. Okay, so majority of, and you think about this as a budget. So something in, energy in is the solar radiation. Solar radiation is enormous. So solar radiation, normally we said it's the 1 kilowatts per square meter, something like that. It's actually 1,300 something watts per square meter. And those solar radiation can power things like wind, rainfall, ocean currents, waves, and rest of hydrologic cycles, and photosynthesis store those energy in organic matter or fossil fuels. So fossil fuel basically is the ancient solar energy. Okay, so the amount of power from the Earth, from the sun, is, we're talking about 174,000 terawatts. 174,000 terawatts. Human these days consumption is about 10 terawatts. So compared to this solar energy, this is human consumption is very tiny. So these energy is about 99.985% of the total. Then there's about 3 terawatts like predicted by gravity, tides, Earth's rotation. That's about potential energy, about 3.02%. This is energy. So energy mostly comes from solar radiation. Then there's a gravitational energy, Earth's rotation. That's only a small 3 terawatts. Okay, and thinking about this, all this energy from the sun is actually much more than what we consume. And even the wind, they have hundreds of terawatts of wind energy, rainfall, ocean current, all of them actually much higher than what human consume. Okay, and these are energy resources. And also, Earth internally also has energy drive the technological cycle, like the volcanoes, the geothermal heat. They're about 23 terawatts to the zone. That's also higher than what consumed. Okay, so energy from the deep part of the Earth are actually enormous, actually more than we need, and also solar energy is so much solar energy. This is basically, and it's the energy budget on Earth's surface. So from this point of view, is that you can see that energy is actually not a problem, especially solar energy, geothermal energy. These are all much higher than even parts of the solar energy, like wind energy, the hydrological energy, for instance, all produce lots of energy, which actually more than we need these days. Okay, so first we look at fossil fuels. So fossil fuels is essentially including things like coal, oil, and gas. This is related to geological cycle, and they are solar energy originally stored in organic matter. And organic matter buried, preserved as fossil fuels. So it's related to geology and stored in subsurface rock material, including coal, petroleum, natural gas. They have significant impact from exploration, production, processing, and distribution. So we're going to first look at the fossil fuels. So first one of fossil fuels is coal resources. America has more coal than any other fossil fuel resources. So in America, in China, in Russia, coal is also the #1 resources because they are enormous amount. And in the United States, they're about 20% of total U.S. energy consumption. And the United States has more coal reserve than any other single country in the world. And about a quarter of the well-known coal in the world in the United States. There are large coal deposits can be found in 38 out of 50 states. So a majority of 70% of the United States, the states in the US has coal resources. So how the coal is formed? So coal basically transform plant matter in ancient swamps, in estuaries, and they start with this swamps. Okay, coal swamps. Basically, you have forest. Then you have when they die, they bury it a little bit. They form peat. Okay, and then the form peat, they have to have something we call that they bury it in anaerobic conditions, which means that the oxygen deficient. Anaerobic means oxygen deficient. They have to be buried. So therefore, those organic matter is not completely oxidized. So then they buried and they will form something called peat. Okay. And the buried peat enter sediment formation, and they cut off all the oxygen, stop the oxidation processes. And with time, the hydrogen will gone in organic matter. Then the carbon will be concentrated. And at a certain point, under pressure, some kind of temperature conditions, they will turn into coal seams in this case. So sediment formation originally was a forest. Then when they die, they buried, and then you have sediment formation. You have rocks on the top. Then these organic matter slowly being oxidized. The hydrogen is gone. Then the carbon is concentrated. Then eventually will turn into coal. And a lot of times something related to like sea level rise. Originally was on land. They're forest. Then by the time the sea level rise, they cover the region. Then you have sand. They have deposit sediments there. Then they bury the peat. Eventually will turn into coal. So, if we look at the different kind of coal, here are how we sort of categorize, classify the coal from depending on two things, depending on how much carbon, how much calorie they produce, like the heat. And the second thing is how much based on the sulfur content. So if we're based on how much heat to produce, the word kind is called lignite. Then it's this bituminous coal. Then it's bituminous, and the anthracite. Anthracite and bituminous are the best quality of coal. Okay. Then sometimes you can depending on sulfur, low sulfur, medium sulfur, and high sulfur content. And we really want low sulfur content, which would be cleaner. Okay. Typically, higher content, carbon content, they will have higher calorie ratio. That will have less volatile gas, and then less moisture content, and sometimes we did run into the coal sulfur content as well. So if you look at word reserve, we say that in the United States we have a lot of reserves. So here is basically a picture distribution of the coal. You can see that the good ones, the anthracite and the semi-anthracite, are occurring in the east, okay, in the Appalachian basins. Here, very good coal, Pennsylvania anthracite, very famous one. And medium high volatile bituminous coal, those are good quality ones here in the east, the center and east, and also some in the in Colorado and this region. Those are good quality ones, and then the poor quality one, like lignite, happening like Texas and there's the Gulf Coast lignite. That's poor quality of coal, and also northern Great Plains region. These are the poor quality ones. They are relatively evenly distributed throughout the world. In the United States, there's about 25% of oil reserve. The annual global consumption is about 5 billion metric tons, and world reserve is about 1,000 billion metric tons, because you can calculate that the coal, if we all use coal, that's probably gonna be good for about 200 years. If you look at global distribution, here are the global distribution: 246 billion metric tons in the United States, and then it's about 272 in Russia, Europe, and Eurasia, I would say. Then it's about 259 Asia and Australia. Okay, and then you see that there's not a lot in South America and Africa, and there's a reason for that. So, but China, United States, and Russia account for about 50% of total CO2 released. But they count about 72, if we add together, about 72% of the world reserves, of coal reserves. Okay, and why they happen in mostly in the northern hemisphere. So this is, if you remember we talked about plate tectonics. This is related to that because in the beginning there was the thunder drift, so they have a Pangea, and at that time, and these north mid latitude place, it was actually in equator. Okay, so therefore they are tropical forest, and then they can be buried and later turn into coal. So the time they were tropical forest, and these days, because con drift, they moved to the north. Okay. So mining coal. So if we talk about the impact of coal consumption, there are two things. One is the mining, coal mining. If we talk about exploration for all the fossil fuels, does not make a lot of pollutions, actually. But for mining, it causes a lot of problems. For example, there's two things. One is the land disturbance from open pit or strip mining. So these days we actually, for coal mining, a lot of time we use this kind of what's called open pit. Basically, they're like a soil. They just use this using very big machines to basically thinking about digging out the formation, and then we call that open pit. Basically, it's all open, is on the surface, not underground. It's open pit, or sometimes we call it strip mining. And then, so these are the way to do that. And this is first kind of problem. So we call it strip mining. This actually started in late 19th century and steadily increases because these are relatively cheaper way. As a result, from surface mine or west of the Mississippi River, we're almost like using this kind of strip mining, and we can have mountaintop removal also become very often, and they are mined from top of the mountains, and the wheat rock from mining placed in valleys. Later, we'll see that this can cause problems, and coal sludge produced by is stored behind the coal waste sludge dam. So later, when it's filled, it can be a huge problem. And also, the U.S. coal classified by sulfur content, like Appalachian. So 0.0 low sulfur is always good, and so West Appalachian, they have very good low sulfur coal, whereas high sulfur coal in interior and also Appalachian, and also has the greater sulfur. Later, you'll know that the high sulfur, when they're burning, they will emit sulfur dioxide, then later can cause this acid rains. So that can cause air pollution and also have acid rains, and it can have trouble in ecosystem. Next, I want to show you strip mining. This is the one big machine, I think, in Germany, and then you can see that how big the instrument is, and then they are so basically this is a huge instrument. So here's a wheel, and then here are like a little pocket, and here's the assembly line. So every time when they turn spins, and here is a big truck. So like conveyor belt from the place is mined and to this place. So here is open pit. It's a huge area, so here it's interesting machine. So here a lot of pocket, and they just grab the the coal. And then when they turn to this side, they drop to a conveyor belt right inside. And then here is empty. And then you can see there's a conveyor belt, and then it moves all the coal and to move around. So here is basically taking up the coal. It's pretty loose. And this is an enormous machine. And then it's going towards here, the beginning. And you can see there's a conveyor belt here. So all the coal dropped here, and then they're going to this side, and then there's a huge truck, and they load into the truck, then the truck will move away and carry those away, and some of the debris of the coal. Okay, the far end, these are all the windmills. All right, so there's lots of impact of coal mining, and in the very humid area, when there's a lot of water, then it normally has a problem, something we call that the acid drainage, mine drainage. And if we have abundant rainfall and the surface water, they can infiltrate the spoil banks, and the material left after coal and other minerals have been removed. They react with sulfide minerals, and such as pyrite, and produce sulfuric acid. Once they turn to sulfuric acid, it becomes very acidic, and then they go into the streams, pollute the streams of groundwater, and also can dissolve heavy metals that cause huge problems. So acid drainage can be minimized through proper use of water diversion practice, or collect the surface runoff and groundwater before they enter the mine area and divert around. In arid and semi-arid regions, water problems associated with mining are not as pronounced as the wetter regions. But the problem is that because the mining activities, you can have problems like exploration and road building. They can be sensitive, and then you can have dust and so forth, then can cause other problems. The future use of environmental impact of coals, because more and more land will be strip mined, and also could have problem disposal of coal ash. The federal guidelines say that all strip mining of coal in the United States has to be restored to support its pre-mining use. And restoration including disposing waste, contouring the land, and replacing vegetation. So here's an example of reclaimed land at the Trapper Mine in Colorado. And the foreground just had the soil replaced after mining here, and the veg side had been entirely reclaimed. So in the United States, they have very strict rules. After mining, strip mining, you have to change the soil and also put the vegetation on it. So this is law. The regulation prohibit strip mining on prime agricultural land and give farmers and ranchers the opportunity to veto mining on their land, even if they don't own the mineral rights. Underground mining of coal and other resources also produce hazards and can cause environmental problems. So the disposal of coal ash, and that's probably 20% of original coal. That's also a problem. And last year, I heard the colleagues from Israel, they are for all the coal ash, they actually was able to recycle them and use them as some kind of building material. And it's pretty neat method. They are recovering all those coal ashes. The mining, processing, disposal of mining waste, shipping, burning, and disposal ash, it can all have potentially adverse to environment. The fly ash from burning, finding ground coal in power plant, they're very hazardous. As I mentioned before, in Israel, they have like pretty high recovery rate. They can making as the building materials, also building road, building constructions. Of course, before then they have to treat them. So yeah, fly ash. The also there's probably several billions of metric tons of coal burned nationwide, worldwide, then release CO2 into the atmosphere, and we know that CO2 is the greenhouse gas, then can have lots of problems. China, United States, and Russia, they are the major carbon dioxide contributor. So in Appalachian Mountains, so there are these kind, we talk about strip mining, we're mining the hilltop. So here I'll give you some examples. The waste material is called coal sludge or slurry. It's generated by processing coal. It's very thick sludge composed of water, with particle coal, rocks, and clay. Basically, it's like you're thinking about this coal mud. It's often stored in impoundments between a dam. Normally, what happens is what the people do is that this is mountain, contains coal, this is coal bed, and they're mining on this hilltop. They mine, and then they dump some of the coal sludge into the valley, it's a pool, and then they build some kind of dam and to protect this part of this hilltop, because eventually these will be mined away. So if you don't have this, it will eventually cover the site. However, you can have lots of different kind of problems. This coal sludge impoundment or coal sludge pool sometimes can fail. For this example, this is a coal sludge, and this is abandoned mine, and for some reason leaked into the abandoned mine and going spill from the mine, going downhill, and then it caused a huge pollution. And this is a coal waste dam on Colorado Creek, West Virginia, failed in 1972, and resulting flood killed 118 people and destroyed about 500 homes. These sludge are like a hollow lava in the volcanic hazard, so it's like a mud, and contains all its coal, and then the downslope flooding, and then it can destroy, making huge problems. All right, so another kind of fossil fuel are oil and gas. Oil and gas, ONG, they're hydrocarbon due to chemical composition of carbon, hydrogen, and oxygen, and then include the oil, and also the gas will be methane gas. They are also formed from transformation of organic matter, and oil normally we call that crude oil, and natural gas are hydrocarbon made of carbon, hydrogen, oxygen. Natural gas is mostly methane, and methane normally made up about 80% energy gas present at a location. Other natural gas, including ethane, propane. Propane is the one you go to on the camp, and that's helping make fire. Butane and hydrogen, those could be the gas. Like coal, they are hydrocarbons. They are also fossil fuels. They're formed from organic matter and escape completely decomposition, and after burial, they are found in concentrated deposits, can be heavily mined from production wells, and they can also be found in oil shale and tar sands. So here is an explanation of how geology of oil and gas. So normally the oil and gas have formed next to water, and so sometimes it relates to phytoplanktons, marine organisms. They are the process of this is actually not yet well understood. But most earth scientists accept that oil and natural gas are from organic matter buried from with marine or lake sediments. So it can be lake, it can be sediments. So first, you should have organic debris, for example, in the this kind of estuaries and basin. And then you have organic matter, pipe production, then they buried. They have to be rapidly buried. Also, it has to be anaerobic environment. Then you can have two kinds of transformation. One is called biogenic, or there are bacteria, anaerobic bacteria. They can consume some of the hydrogen, and then they transform this organic matter into oil. And because they're phytoplanktons, they will not form like trees, they will not form coal. Instead, they will form oil or natural gas. And with time, and they basically trapped in some locations over a long time, then it will do that. So the plants in swamps may form coal if buried, but this in the ocean, marine environment, or lake environment, these organic matter, they will be buried and increase in temperature pressure. They will eventually turn into oil. So here are some examples. So this is water nutrients with no oxygen on the top. Very important. You don't want to have oxygen. And then somewhere here you have the thermogenic gas and crude oil formed in some rocks here, which are enriched in organic matter. And these, we call that reservoir rocks. They are porous and permeable rocks. They're like sandstones, they're like groundwater. So you can store, and these kind of reservoir rocks, they can store oil and gas. And sometimes you have a formation like this, you have an anticline on the top, you have a cap rocks. These cap rocks are normally impermeable as barriers for to trap these oil and gas in place, forming oil field. And so here is the same thing. This is impermeable shale on the top, and then these organic matter they accumulate here, and because they have cap rocks, they can store in this reservoir and without getting licked up. So the production of this oil and gas normally through a well. So you and through this anticline, normally you drill a core, and then because the end of pressure, the oil will come up automatically. So there are two kinds of recovery process. One is called the primary recovery. Basically, you use pump to pump those oil out, and normally it's no more than 20% of petroleum in the field and enter natural reservoir pressure. Then it's not going to be complete. There's two things happening here. Number one is that even though this is kind of formation, there's a storage rock. But sometimes those storage rocks is not interconnected. Okay, so therefore, even if you drill one hole here, one core here, and cannot guarantee all the oil come out, and you sometimes can drill multiple of those and then increase the cost. And then these days we have, last time we mentioned that we have enhanced recovery, which means that we sometimes inject gas and liquids, and then we can displace those oil out, pressure them out, and we can reach about 50 to 6% of petroleum. And then you can see that there's still 40% of petroleum still cannot recoverable. So this is, its efficiency of recover those is very, very important. So here is this anticline trap, can trap there. Sometimes you can have a fault zones, and then you can trap the oil, and in here, sometimes have inconformities, and you can trap them oil here. So these are the places for geologists they're looking for, whether these are places you can trap oil, and these days you can use the artificial earthquakes. You can, and because the S waves, the second wave cannot go through liquid, so you can use that to determine whether some places are liquid and then help you to decide where are the oils are. Okay, so commercially, oil these days is produced almost exclusively from sediment rocks deposited during the last 500 million years of the Earth's history. Almost about 85% of the total production is in less than 5% of production yield fields. For example, you can see that majority of them is here in the Middle East. Very interesting. About 62% of total reserve. That's billion barrels. Africa has some of those. Europe and Eurasia has some. And South America actually has quite some. North America does not have lots of oil. Instead, they have, because they were on land in tropical forests, they have coal, more coal than oil. And this Asia, Australia has little. Okay, 85% of the total production in less than 5% of the production fields, mostly in in the Middle East. 65% of the total production from about 1% of giant fields. And most giant oil and gas fields near recently active plate boundaries in the last 70 million years. So most of the world's giant oil fields are located near plate junctions that are known to have been active in the last 70 million years. Okay, next one is natural gas. Natural gas is relatively, it's had larger global reservoir. You can lasting about 100 years at current rate of consumption. And there's most reserves in Russia and Middle East. And natural gas is relatively clean fuel compared with coal and oil. And it has potential to replace oil and coal in the transition from fossil fuel to alternatives. The reserve global reserve can last about 100 years. The coal lasts about 200 years. And then we have different forms. There are natural gas, it's very large. And then these days we actually have something called methane hydrate later. We'll talk about this. So the first kind of natural gas is the coal bed methane. Coal bed methane is the coal contain a large amount of methane. In fact, when people mining coal, one of the hazard in the coal mine is actually methane gas. But in old times we cannot use them. These days, because technology, the methane reserves in Wyoming, that's sufficient for U.S. natural gas use for about 5 years. But most coal bed methane is shallow. They are economic to drill, and but they have concerns about transportation and processing process. So basically, so there are, although the coal bed methane also have some environmental problems associated with production. And one of the problems is that when you drill them, they have salty water come out, and salty water may contain groundwater. So how we're going to dispose those salty water is a problem. This methane is a flammable gas. It's flammable, so it has problems when you're mitigate methane, especially when it's away from well sites. When you do this kind of coal bed methane, sometimes we have reduction of crop productions if we use the salty water to irrigate the crops. It can have pollution to the stream water, loss of spring flow as groundwater. Sometimes the erosion or the runoff of land distribute for roads, well sites, processing, transportation, methane. These are some of the problems that's related to coal methane. Another one is called black shale gas. This is pretty recently very economical and black shales. And here is the Marcellus shale in Pennsylvania. So these are very famous. So these are called black shale. Most are Devonian shale, buried about kilometers from beneath northern Appalachian Mountains. They contain about 500 trillion cubic feet of natural gas, which is about 10% of potential resources. All these, we sometimes call these black shale gases tight natural gas. They are distributed between small tight opening throughout the black shale. Shale is mostly made of clay minerals, and clay minerals have pretty high porosity, but does not have high permeability. So the natural gas can store it there. Then in conventional ways, we cannot sort of tap them. And so the tight gas is basically an uncontrolled reservoir compared to conventional reservoir. They're pocketed in these geological structures, and the famous one is the Marcellus shale. So how that works? So this tapping these black shale, the shale gas is unconventional gas is a lot of to do with the technological improvement. And then it used to be like the when we drill ground, we have a drill only can go straight down. Okay, so one of the biggest invention is the horizontal drilling, which means that you can drill down to a certain depth, actually shale depths. You actually can drill horizontally. So when you do that, when you drill horizontally, then you have within this bed where they store a lot of methane gas, coal gas, methane gas, and then you break the shale so that all the pocket between those clay minerals, they can be released, and then they can come out as a methane gas. Without this technique used old days, you cannot tap those gas. So they use a technique, something we call fracking, hydraulic fracking. Use water, chemicals. Then basically the idea is to try to break these rocks, and also have electric shocks. So the rocks is braked, and then little gas will be released, and then coming through this production well, then will be recovered, and then the depth is about 1 to 3 kilometers deep. And the famous ones, Devonian Marcellus shales. Now, the concern about this shale gas are, so the methane reserve in the West Wyoming sufficient fuel as natural gas for 5 years. Then there's concern over extraction, processing, transportation. The well needs lots of water, and chemicals also use part of the extraction processes. So there's a huge amount of wastewater produced for this fracking processes. Simple thing is in the Pennsylvania alone, 34,000 cubic meters is about 9 million gallons of wastewater per day was produced in 2009 by gas wells in Pennsylvania alone. So the natural water in the shale where gas is extracted may have contaminants such as the metal, cadmium, benzene, and methane, and also these the draining flood. The draining fluid can contain wastewaters at surface. The one to show you Those are the draining mud. They look at the color. These are can be contaminated. And the salty water can corrode equipment in power plants. And also people said that because they're deep enough, these water can contaminate the groundwater. So some people reported that the dishwashers were malfunctioning, and then they have problem with their drinking water. So these, have lots of debates. Whether you can have problems. And EPA are, being asked to study the safety issues associated with draining of natural gas, and actually New York is sort of banned, upstate New York, because our water supply is actually coming from upstate New York. So therefore, we actually banned upstate New York to do the fracking, because they are afraid that the fracking, the fluid can contaminate groundwater, then change the quality of our drinking water. Okay, so here I'm going to show you a little video about fracking. As you can see that it's controversial, and the fracking, as people are still debating, and the fracking, and this Michelle, I forgot to mention that people record that there's earthquakes, small earthquakes, not big earthquakes happen during fracking, because so that's the problem. Okay. Methane hydrate, also another kind of methane, but methane hydrate is actually solid. That could be a good source of natural gas, and that exists at depths of about 1,000 meters. So methane hydrate is basically a white ice-like material composed of molecules of methane gas surrounded by frozen water, ice. So they actually mixture of water, methane and water, and at low temperature turn into ice. Beneath the sea and under permafrost land area, about 1,000 meter to 1,000 meter, 1 kilometer. So the reason is that they need pressure, high pressure, cold temperature to compress water and methane together for mass. So this the problem is that the exploration production is pretty complicated because it's under water for kilometer. So how to pressurize at very high pressurized conditions needs lots of study has to be done. There's also a video showing what is methane hydrate. Okay, so this is the hydride. So this methane hydride-based deposit are found throughout both Pacific and Atlantic Ocean, and it's a very potential resource. Problem is how to, as the professor said, that how to produce them and economically export them. That's the sort of key. So here's another video. I just want to show you. Okay, so good idea. So the lots of those in Alaska or in Canada, it's frozen and a lot of methane. They accumulate in lakes, and a lot of times because of the narrow and anaerobic bacteria, they consume organic matter, decompose them, and then forming methane. And then because it's cold, they can frozen, and if it's high pressure, like in Pacific Ocean, they can be at the bottom of the ocean floor, forming methane glycerate. But if it's just cold, then they can frozen in ice, and then it shows when you drill a hole, then the gas come out, and then you can start to make a fire. If you light up, you can light up. Okay. So well, when we drill oil or gas, then they can have impact of exploration and production. And first of all, you have land disturbance, you have access and drilling, we have environmental impact,
So, for example, when you're building roads, conducting floor gratings, building supply lines to a remote area, and then you can cause impact. The development of oil and gas fields, to drill wells and land beneath the sea, disposing wastewater or brought to surface. And also, each steps there are potential for environmental disruptions. And for example, there could be serious oil spill along the coastlines of Europe and North America. It can spoil beaches, estuaries, harbors, kill marine lives, and so forth. So as results, the current they can have salty brine water, evaporation with disposal problems. Oil field can develop in sensitive area, and we can have blowout or fire at oil and gas wells, have acid rains, and so forth. These are potential problems. But there's some controversies here. There are people try to start to explore in Arctic National Wildlife Refuge in Alaska. So we're north. So the north tip of that, this is Arctic National Wildlife Refuge in Alaska. And these places have several billions of barrels of oil are located, and people want to mine them. Okay. And if there's, of course, there are many reasons. Of course, the United States need oil. And then if we explore here, then we can reduce the amount of oil being imported. And also, new oil development can bring jobs and economic growth to Alaska and so forth. But then they need new techniques for exploration and drilling. Okay, so I need, for example, there are some wildlife here. How are we going to protect the wildlife without? We can harvest, tap the oil without affecting the life of all those wildlife. So this is actually pretty challenging. So there are several ways people think about to do this. For example, one is what's called directional drilling from central locations, like the shale gas. So we start with the centralized. We only have one site of drilling. Then we go deep. Then we go parallel or sideways to tap the oil field. So minimize the amount of drilling the different sites instead of that. So sort of concentrated central locations, many wells from single site and spread out underground. And so we can do that. So minimize the surface disturbance of the land. Now, the second kind of things is transportation. Okay, so this is once you have this, first of all, you don't want to bury in the land. There's a lot of work and a lot of money cost for that, and also there's it's in the we talk about permafrost, and when that permafrost start to melt, then they have subsidence, then these pipes can have problems. So some innovative ideas, they actually hang this pipes, construct these pipes to hang there, so that the animals can migrate between them, has a minimal effect on them. So it's called elevating pipelines above ground, allow animal for migration, and so forth. And we can avoid construction of permanent roads. The roads are made of ice in winter and well in summer, then that could have some kind of problems. There are also opponents. Even though you have this kind of technological advancement, it's always can have adverse effect. Some wilderness area should remain wilderness, and the drilling will permanently change the Arctic the wildlife refuge. So that's always debates about this. Next kind is oil shales and tar sands. Oil shale is the fine-grained sand and rocks containing large amount of organic matter, kerogens, which can give a substantial quantity of hydrocarbon, and essentially a petroleum source rock, which has not undergone the complete thermal materialization required to convert organic matter into oil. And instead, they actually been stored in shale rocks. And the best known oil shale rocks found in Green River Formation is approximately 44,000 square kilometers in Colorado, Utah, and Wyoming. And they have 2 trillion in the United States, 2/3 of the world's oil shales. So you can actually have oil and gas shales. When they do this kind of work, they're actually using hydraulic fracture as well to make sure the oil will come out. And mining the oil shale and using known technology, of course, is expensive. But as oil price rises, this oil shale mining can be considered. And the tar sand is like this. It contains tar oil or asphalt or other semi-solid and solid petroleum products. So they're not necessarily sandstone. They can be shale, limestone. Normally, you can think of this oil shales are not matured oil, and these tar sands is like over matured. So therefore, the hydrogen is gone. It's not liquid anymore. Actually turned into solid. So in order to recover them, you have to a lot of time draining. We use steam, adding more water or hydrogen to it. So turn that into liquid, semi-liquid, and then turn that back to the petroleum products and come to the surface. And then those are, we call that tar sands. And the famous tar sand is Alberta, Canada. It has 78,000 square kilometers. The one possible conclusion concerning the geology of tar sand is that they form essentially the same way as a more fluid oil, but because much more of the volatiles and companion liquids in the reservoir rocks has escaped, so they are more viscous, will remain as tar sands. As I mentioned before, if we say oil shale is non-mature ones, and tar sands is too mature. Okay, so the future of oil. So recent estimated proven oil reserves in the world suggest that as present production rates, natural gas, oil and natural gas will last a few decades. And but the important question is how long oil will last at present and future production rate, and at what point we reach the peak production. So eventually we'll reach the peak oil time. And right now, about 3 trillion barrels of oil will be recovered, and the world current consumption rate is about 30 billion barrels per year. So the estimate peak production is about 2020 to 2050. The oil production in the United States not extend beyond 2090. So therefore, the most important thing is planning, education, research, and development of alternative energy sources, and for example, gasification and liquefaction of coal and other renewable sources can be very, very important. Okay. Next thing is fossil fuel and acid rain. So fossil fuel is a case that acid rain can be produced as a result of burning fossil fuels, because a lot of fossil fuels contain sulfur. When sulfur and nitrogen being burned, when the coal is burned, for example, they release sulfur and turn to sulfur dioxide, sometimes have nitrogen dioxide. And let's say it's about 17 million tons of nitrogen oxide and 13 million tons of SO2 in the atmosphere, and then they can cause acid rains. So acid rain refers to both wet and dry acid deposition. So for these gases, when they dissolve in the water, then they will, in the precipitation rain, they will become to be the wet deposition and become acid rain. But sometimes the particles containing acid precursors can fall on Earth's surface, then react water to produce acid. Then we call that dry acid. So deposition. So both dry and wet acid deposition are called acid rain. Okay, so acid rain is defined as the pH is below 5.6. Why is choosing 5.6 is because the CO2 in the atmosphere, when they dissolved in currently dissolved in water, it will change the pH about 5.6, 5.7. So if it's lower than that, it suggests there's a contribution from SO2 or nitrous oxide. And acid rain is the original to global environmental problem. It contains both wet and dry acid deposition. And here is in the United States, so a very high sensitive area, the East Coast and West Coast, low sensitive area in the middle, in the central part, mountains. They are not very sensitive acid rain. So so they are, but they say majority of the West Coast and East Coast and West Coast, they're very sensitive to acid rains. Acid rain can cause major environmental effects like damage to vegetations, damage to lake ecosystems, and especially in forest, as the evergreen trees in Germany and red spruce trees in Vermont, and the soil fertility may be reduced. The nutrient can be leached out by acid, and the acid releases toxic substances into the soil, and this can have trouble for vegetations. Acid rain can also damage lake ecosystem. It disrupts life cycle of fish, frog, and catfish, and so forth. It can also damage buildings. This is a structure monument, and it's made of marble, and the marble can be dissolved by acid rain very easily. So you can see that it's not as good as anymore. So sandstone, marble, limestone, they can always dissolve. So what are some solutions? Solutions are periodic additional buffer material like calcium carbonate into the lake. Short-term effect, also quite expensive. The better way is reducing emission of chemicals, and we can treat coal before, during, and after burning. Then it can help to us to resolve this acid rain issue. The next one is nuclear energy. Nuclear energy is basically we use nuclear energy, relies on fission reactions. So nuclear fission basically is a splitting of atomic nuclei by neutron bombardment, and the released neutron will struck other. For example, you use uranium-235 as an example. So if it's 235, so when they bombarded by neutrons, they will split into fission fragments like cesium, strontium, and noble gas, and then emit more neutrons. Then more neutron hit another uranium-232, then more they will split, and then they hit the neutron will split more. So in this example, one uranium-235, when they split, they actually emit 1, 2, 3, 4 neutrons. One coming actually produce 3, and then one will produce 3. So it will have catastrophic, it's called chain reactions. Okay, so then more of these uranium-235 will be split up. And this is also, as more and more uranium split, it release more neutrons and then produce more energies. If this kind of process is controlled, then we can use to produce energy, produce heat. But if this is uncontrolled, it turns into nuclear bombs. Okay, but most of there's currently 440 nuclear reactors that's provide about 60% global electricity needs. In the last 10, 20 years, there's back and forth in Europe, especially in Germany and French. In Germany, there's people on strike and try to get rid of nuclear reactors because of the health, the environmental risk. And most of the uranium is fission in the nuclear bomb is from uranium-235. Naturally, abundance is about 0.7% of concentration naturally. So after you get uranium mine, you have to sort of enrich them to about 3% at least before we can use in a reactor. But the fission reaction produce a huge, it's very high density of energies. Fission of 1 kilogram of uranium is equivalent to burning about 16 metric tons of coal. So 1 kilogram versus 16-ton metric coal, that's enormous. So the first controlled nuclear fission was actually demonstrated in 1942, that leading the first use of uranium in explosives and also as a heat source that provided steam for electric generation. And so 1 kilogram was about 2.2 pounds and release about 16 metric tons of energy. So here is that in the nuclear energy, there are radioactive decay. So it's alpha decay, which is emitting alpha particles. There's beta decay, that's emitting electron, and gamma decay is emitting gamma rays. And for each one of them, they have a half-life. Uranium-238 has a half-life 4.5 million years, and 234, which is the products of decay of 238, is 24 days. And then uranium 234 has a thorium 234 is 24 days. Uranium 234 is 247,000 years, so forth. The average natural concentration of uranium is about 2 ppm. And then we have to find mines in different places to concentrate, which has been concentrated to 400 to 200 to 2,500 times before we can use mines proper. There's 3 types of common deposit: sandstone impregnated with uranium, the veins of uranium-bearing materials, and also placer deposits. Okay. So in universe, the uranium is about 0.2 ppb by weight. In the sun, it's about 1 ppb. Meteorites at 10 ppb. Crustal rocks are actually more rich because uranium is incompatible. They are like to be in the melt. And seawater only 3.3 ppb. Streams about 0.04 ppb. Humans actually 1 ppb. Sometimes, some juries. So these days, normally we use the burner reactors for making a nuclear plant. So burner, they consume more fissionable material than they produce. We call that burner reactor. They consume more fissionable material than they produce. So during the fission reaction, they produce more fission other nuclei. So this is, they consume more. There are 4 components of burner reactors normally. They can have a core, okay, a control rods here, a coolant, and the reactor vessel. So typically, the core reactor, the main reaction taking place, is contained in a heavy stainless steel reactor cell. And for the increased safety and security, the entire cell will be reinforced concrete building called a containment structure. Okay. So here's the core. That's the reactor vessel that is containing the structure. Fuel consists of small ceramic enriched uranium we're putting here. And then for the reactor to operate, then you have control rods. That's basically is a neutron absorber. So when they put into this reactor, then they will absorb neutron. They will slow down the reaction. When they take out, then the neutrons will bombard other uranium-235. Then this will continue accelerate. So you can use this control rods to control this speed. So we need to have a minimum concentration of fuel, uranium-235, for the chain reaction to be self-sustained, or we call it critical. And that's very important. Then once the heat produced in this reactor or the core, then we use a heat exchanger. Normally is the pressurized liquid. Sometimes they use all kind of liquid. Sometimes basically has to have a very high heat capacity. So use coolant. Those are being heated up in the reactor and transported into the heat exchanger, where they can produce steam. Steam then driving turbines and making electricity. And this is the nuclear reactor. Then some will have condenser, also make hot water, steam for water. And then the hot water can also be used. And then this is sort of heat exchanger. This is the pressurized cooling system. So it's called that passively safe. And now these days, people use gas cooled reactor, pebble bed reactor, we call that instead of burner reactors. In the next few years, preventing risk of core meltdown, providing optimum energy production. But they use gas cool this reactor rather than this liquid. And liquid need to pressurize and also have circulating water to take the heat out of this reactor. If the heat accumulates in the reactor when the temperature is higher, because it's using stainless steel, so higher than the melting point of stainless steel, about 2,000 degrees, then it'll start to melt. And then we call that a meltdown. Then it can have a huge problem. Then in the core, the radioactive element, isotopes will be leaked out, and then they can have contaminations. Okay. So the risk with fission reactors, there's various amounts of radiation to the environment from mining, processing, transportation, and also before transportation. And nuclear reactor accidents happened many, many times. Even though people build this for very sick, they did as much as possible. These days it's also improved. designs to help to control the system. And then as always, something can happen. So the famous ones are several of them. Like the first one is the 3 Mile Island in March 28th, 1979, near Harrisburg, Pennsylvania. That's one of the most serious events in the history of U.S. So the nuclear power occurred. This problem occurred on March 28, 1972, and the malfunction of valve and the human error at the nuclear plant resulting in a partial core meltdown, and then they released radioisotope in the environment, and intensive radiation was released in the interior part of the entire structure. Its function as designed, only very little small amount of radiation released out in the environment. So as you seal all this reactor building, then you can keep this radiation inside. Okay, and another famous one is Chernobyl. Chernobyl, it was happening April 26, 1986. Its time was Soviet Union's like level 7 so it started with the workers at a nuclear facility in Sweden. They find there's radiation in their nuclear plant, and they couldn't find where it is. And then they painstakingly searching for the source of elevated level of radiation near their power plant. And then at the end, they conclude that it's not the Sweden, it's not their problem. It's actually from Soviet Union, and they blow it by the wind. They find, and then the Soviet Union at the end finally admitted that there had been accident at their nuclear power plant at Chernobyl on April 26. It was the first notice that worst accident in the history of nuclear power has occurred, and that's believed that is because the supply of water, this cooling water, always what happened is always the cooling water is a problem, and cause the temperature of the reactor core to rise over 3,000 degrees, and then melt the remaining fuel. Then afterwards, the explosion blow off top of the building over the reactor. Then the graphite surrounding the fuel rods ignited. The fire produced a cloud of radioactive particles that rose high in the atmosphere. And then there's many people, there's 27 confirmed cases of radiation sickness, 31 people died of radiation sickness, and afterwards there's lots of people has been evacuated in their area. Almost 115,000 people in that 30 kilometers zone was evacuated. And about 24,000 people received the radiation dosage several hundred times more than they normally people experience. And then there's also cancers. There's recorded by the time of 1994, there are 132 new thyroid cancer cases and so forth. It's terrible. It's one of the worst things happened. And someone asked me that over the next 50 years, will have been responsible for 16,000 deaths worldwide. And this is, one of the worst problem. Then there's another one, recent one is the Fukushima Daiichi nuclear disasters happening in 2011. This is the picture of that. So what happened was there was an earthquake, and after the earthquake, there was a tsunami, and the tsunami blew rainwater into these places, and then knock off the electric lines, and then therefore they don't have electricity to run this cooling water line. And then they have a backup generator, and the backup generator fails because water going to the basement, and then there's a backup of the backup generator. That one failed too. So there's no way you can run this cooling water and bring the heat away, dissipate the heat. Therefore, the core meltdown. You see, this is after it has explosion fires and cause the radioactive material leaking. And then at the same time, because of the tsunami, there's a lot of seawater running into this core, therefore being contaminated. And then last year, and they after 20, 30 years, after 13 years, 12 years, they finally was able to process the contaminated water, and they start to release those water back to the ocean. And they said that that's safe. So the nuclear reactor, the fission reactors, have lots of problems, and then there's a problem worry about the nuclear weapons, and because this nuclear power plant can produce things like plutonium highly, so that as byproducts of the fission reactions, you can produce highly reactive materials. Then you can use that as nuclear bombs, and also disposal of the nuclear waste. Those could be huge problems. So future of energy from fission, the nuclear power plant produce about 20% of electricity in the US today. About 104 reactors now in operation, more than 80% of East US. Top state using nuclear power, Vermont 74%, South Carolina, New Jersey, and Connecticut. And it's still debatable if US should expand more of this. The benefit of this is they have high energy density, they have no greenhouse gas emitted, there's no pollutant that causes acid rains, but the problem is that nuclear waste could have an accident. So these are the potential problem, So, but if you look at the design and the construction, and it's probably one of the safest thing you can build. The question is that there's always accident, some kind of accident. Like even for Fukushima, they considered the fear of the electricity, so they have backup generators. And then for the backup generator, they have redundancy, they have a backup of backup generators. And this particular event, and none of those are working. So there's always something can happen. The worst case can happen. So therefore, these days, people talk about using gas co-reactors instead of using these pressurized. You need to actually to pump those things and heat out. You have gas, which will be more reliable. Okay, so how we get rid of the radioactive waste? So there are three kinds of waste. So the waste are the byproducts that must be extracted when electricity is produced from nuclear reactors or weapons. It are produced from plutonium. They're low-level waste, only small amount of radioactive substance, can be isolated from the environment for about 500 years. So the way to treat this, we call that dilute and disperse, and we bury them. And the other one is called transuranic waste. Those are human-made elements heavier than uranium, and the isolation for about 250,000 years. So these days we like to bury them in the salt bed. Later explain why we use salt bed to do this. So for high-level waste, produces few assemblage in nuclear reactors become contaminated or clogged with large quantity of fission products that like the steel line concrete contains at nuclear plants. And these treatment of these are actually a geological problem because lots of these radioactive byproducts have pretty long resin time, like krypton, 10.7 years. Strontium 90 is 28 years. Cesium 3 years. Plutonium is 24,000 years. So you have to store them, and then you want them to not contaminate groundwater, for example, and then last there for 1,000 years, and then eventually they will be decayed away, turning to be non-radioactive, and then safely treat them dispose them is one of the big problems. So these days, here is an example in Casbah in New Mexico. There's a deposition site. So they bury these waste into a salt bed, into these places. It's about 600 meters of salt. And one thing about salt bed is that so you put there, and then salt eventually you will seal off this system. And so therefore they will be completely sealed. And the salt bed, they're several hundred meters thick. Therefore, they have less chance to contaminate the groundwater. They're about 225 million years old, and the area is geologically stable with very little earthquake activities. And the salt is very easy to mine, has no flowing groundwater. And so the rock salt actually flows because they have slightly lower viscosity, so they can flow into the mine openings. And then slow flowing salt will naturally close the waste field space and store for this facility in about 100 to 200 years. Then you can seal the waste. And this New Mexico site is very important. And it's the first geological disposal site for nuclear waste in the United States. It's also a pilot project and being evaluated very carefully. And so the safety is basically the main concern. So next thing, I think is the future energy is the fusion reactions. Fusion is combining light elements to produce heavy ones, then releasing energy. And the sun and other star, they are doing this. They are huge nuclear fusion reactions. And the nuclear fusion reaction, they are the research objective. Right now, it's not commercially reality yet. There's very good environment because there's very little radioactive waste. And then there's another supply. For example, we use hydrogen, deuterium, and tritium. They're basically water, contains lots of them. And the only problem is the technology is under development. So here's the video about fusion reactions. Okay, so just last couple of years, there's DOE has mentioned that there's for the first time, the energy they produced for these fusion reactions actually more than they put in. So which is great news to the energy development. But in order for that to be commercialized, it's still a long way to go. Okay. So next one is geothermal energy. So geothermal energy basically extract energies, social heat and pressure from natural hot water and steam. So we know that Earth's interior has energy. Okay, so here is the something we call that. This is the depth in kilometers, 5 kilometers. This is surface heat flow. This is temperature. So these we have something we call geothermal gradient in different places. This is 47 per kilometers, 12 degrees per kilometers. The normal geothermal gradient is about 12 degree per kilometers. But some places, like Battle Mountain area, then you have pretty high heat flows here. And these high heat flows can be used to heat up water and or sometimes even generate electricity at some sites. And there's vast amount. Here are the more of this kind of map. So here's the Battle Mountain and similar places like in Cascade Ranges, actually pretty hot, have high geothermal energy, Southern Trough, and so forth. So many places has high geothermal heat, and then we can use them. The vast majority of geothermal energy resources, there are 500 times of oil and gas resources. Only 1% could be captured from upper kilometers. The idea of harnessing Earth's interior heat is not new. So geothermal power was developed in Italy using dry steam in 1904. It's now used to generate electricity in numerous sites around the world, including a few in the Western United States and Hawaii. Okay, so here are some examples. So the geothermal energy, normally we can have 3 kinds. One is basically just hydrothermal reactions. We make a hydrothermal reaction systems. So normally you have a geothermal basin in which a variable amount of hot water circulates. And then there are 2 basic types. One is called vapor dominant system. The other one is hot water dominant system. Vapor dominant system, hydrothermal system are a reservoir in both water and steam are present. And then near the surface, the pressure is lower. Therefore, then you can turn into vapor. Then you can put a pipe here. You can tap this vapor. Therefore, you can drive the turbine and generate electricity. And the other one is the water powered, and then you actually can heat rocks. So here, so you have like magma or very hot rocks heated, and then you have water. You can pump water through the system, which is part permeable zone. Then you can build a power plant on the zone of low permeability, and then you have injection well, cooling water here, then production well, the hot water will come up. And so overall, this kind of system is environmental friendly with a great potential for the future energy, but it's site specific. Sometimes it's pretty expensive production processes. Then they sometimes can cause pollutions. Sometimes have noise pollution, the on-site noises, there's gas emissions, and then there's a scar on land and so forth. And all the environment problems social with, including on-site noise, and also develop the geothermal energy. Good thing is, does not requires the extensive transported raw material or refining, and like fossil fuel does. But it can produce something like nitrogen oxide, and also produce a little bit of carbon dioxide by coal burning power plants producing comparable amount of power. So they are efficient and then produce a little bit carbon dioxide. It does not produce particulate pollutants associated with burning burning fossil fuel. And the problem of sometimes the water come up or can be saline, can be mineralized, can be corrosive to pipes, pumps, and dispose those water. Sometimes you can inject back into the system, and it can affect the nearby geyser activity, reducing the heat source driving geysers. So in Yellowstone, in some national park where they have geysers, they actually have laws preventing making this power plant. Okay, so renewable energy. Renewable energy, there's many different kinds of renewable energy, including like solar energy, which is rapidly growing. There's a passive and active solar energy. Then there's hydrogen cells. The renewable energy, all these other sources is alternative energies. They can be split into two groups. One is renewable and non-renewable. Non-renewable energy sources include nuclear energy and geothermal energy, and renewable energy, including things like hydropower, hydrogen, wind power, and biomass. Renewable energy is non-exhaustible, of course, and they always associate with minimum environmental degradation, and except burning biomass. Solar energy is directly used through passive solar systems. There's passive solar system involve design that enhance absorption of solar energy and taking advantage of natural changes. There's active solar energy. Sometimes we have the three things, like first one is solar collectors. Solar collector are usually flat panels, and as you see that a lot of people use that for generate hot water. And normally you have a glass plates or a very black background where water is circulating through tubes. Solar sunlight will enter the glass and absorb by the black background. Then they can heat water in the circulating cubes to 30, 40, 45, 50 degrees, sometimes can reach even 90 degrees. Then you can use that for household use. You can take showers and or washing clothes and so forth. Then this is for continued growth. The second one is everyone knows is for voltaics, and basically it's a semiconductor material using it's a photovoltaics, and they can absorb sunlight and turn that into electricity. So this is a solar. And then the next these are used to be very expensive, and these days it's getting better because more production of the solar panels, and it's increasing like 35% a year. Okay. Solar energy and environment normally is rather low impact on the environment. The major disadvantage is the solar energy is rather dispersive, which means it's like low density of energy. So in order to collect lots of solar energy, you need a huge amount of land. So which can be done by combining with existing structures. For example, adding solar panels on heaters or roofs and existing buildings. Okay. Next thing is that hydrogen fuel cells, and hydrogen is also high quality fuel that can be easily used in any of the ways in which normally fossil fuels will do. And it can use to power cars and trucks, engines, and also you can use fuel cells and hydrogen fuel cells and similar to batteries that can produce electricity. Hydrogen is clean fuel, and the combustion products of this burning process is water. And so it does not contribute to global warming, air pollution, or acid rain. And right. So in many places like Hawaii or Europe, and they're talking about turning to like wind energy or geothermal energy into hydrogens, which can be transported to other places, export that energy in the form of hydrogen to other places. And it's a pretty promising renewable energy. Okay, next one is the water power. So water power is the ancient source of energy. Water has been systematically used as a source of power, at least since the time of Roman Empire. water wheels were turning west in Europe in 17th century, harnessing the energy of moving water and converting to mechanical energies. And during the 18th and 19th century, large water wheels provide energy to power grain product mills, sawmills, and other machinery in the United States. And these days, we can use hydroelectric power today, and that provide about 10% of total electric energy in the United States. And it's expected to increase somewhat in coming years, but there are problems, especially these days. They have some problems. So smaller hydropower, normally it's like 100 kilowatts, are we call that micro hydropower system, are actually more popular than the big ones. Now, the problem of the bigger ones are the following. Number one is that we talk about this, you have to build dams, okay? And while you're building dams, then they trap sediments that could otherwise reach the sea, then replenish the sand on beaches, then they have problems. The water falling over the high dams also sometimes can trap nitrogen gas, which is nitrogen gas in air. The nitrogen can enter the blood of fish and expand and kill them. And also the dams to harness water power can also cause displacement of people, loss of land and reservoirs, loss of wildlife, and change the ecosystem. So here shows the Three Gorges Dam on China Yangtze River, and this is one of the biggest dams. It's completed in 2006, and that displaced more than 1 million people from their homes. They drawn in 13 cities, 1,300 villages, farm fields, archaeological sites, and highly scenic river gorges. The dam is about 200 meters high and more than 1.6 kilometers wide. And then it's about 2010 it filled, and it took several years to fill and produce a reservoir about 600 kilometers long. So the positive thing of using power is there are in these three gorges, they have 26 giant turbines. They produce about 18,000 million watts of electricity. That's probably equivalent to about 18 large nuclear or coal burning power plants. So it does make a huge, enormous amount of electricity. Negative thing is that they contribute to destroy the ecosystem, like extinction of Yangtze River dolphins, the habitat for many other plants and animals, and the loss of species diversity. And the people are also concerned about the water can be polluted by raw sewage and industrial pollutants then in the river, then because it's a long river, and then they can have a huge impact over the region. But so there's some people, because some people argue that we actually the Chinese should not build this big long river big gorge dam. Instead, they can do, the tributaries can build smaller dams, then they can do this, probably produce same amount of power than without making the big dams, electric power plants. So this is one of the case study. You can see that this is big dams, not controversial, especially big dams. It's controversial. Next thing is, another thing is the tidal power. So there's people using tidal power with tidal power. So some places, when there's the high tides and low tides, ocean tides, and you can build like a reservoir. When there's high tides, you let the water come into that pore reservoir, and during low tides, then you're it's like a lagoon, we build a lagoon, and then you have turbines. When there are low tides, you release the water going to the ocean. Then you have a relative differential height differences. Then you can use that and generate electricity. So basically, it needs a favorable topography, like a Bay of Fundy region in northern United States and Canada, and tides of Bay of Fundy has the maximum rise about 15 meters, and minimum rise about 8 meters. Then you have 8 meters of high tides, and then you have that differential differences Then at high tides, water will moving into that reservoir, and at low tides, it release the water back, and during the process, it generate electricity. So this is also promising. Next thing is the wind power. Wind power, the less than 1% of electricity demand, but 10% potential in a few decades. Wind power, like solar power, evolved over a long period of time, beginning with early Chinese and Persian civilization. Wind was propel ship and driven windmills to grind grains and pump water. More recently, wind has been used to generate electricity, and basically the generation of wind is differential of wind pressure, and wind pressure is differential of temperature. And when it's hot, then the air more buoyant. And then when it's cold, then it's cool, have high pressure. So that's drive the wind. Okay, wind. And on a national scale, the areas of greatest potential wind energy are the Pacific Northwest coast area, the coast region of northeastern United States, and the belt extending from northern Texas through the Rocky Mountains, and also the Indiana and Illinois, and those are good sites. The mountain areas of North Carolina, the northern South California, and also Chicago is called Windy City. They all can have windmills generate electricity. However, there's different places. For example, you have top of the mountains where you have bigger wind, and steep cliffs, you have a bigger wind. And then between mountains, you have a pass that's you can put a window there, and that's a place to generate electricity. Okay. The advantage of wind is widespread, abundant, inexhaustible resources. Wind power has become an inexpensive source of energy. It's competitive with coal, but less expensive than nuclear power, but more expensive than natural gas. It's a clean source of electricity and does not cause pollution and release carbon dioxide, and that change climates. But the adverse effects, including things like it can make kill birds, especially large birds of prey, like hawks and falcons. They fly into blades, and then the large wind turbine farms require land for roads, wind turbine pads, and other equipment. And wind turbine may degrade an area of scenic resources. And this is the reason that people want to, for example, put the turbines in the Martha's Vineyard. Those are on the coastline, the Vineyard Sound, Lion Sound, and then it was debated and then was canceled because they're going to change the view. Let's say that they change the view, scenic resources. Tall wind turbine may interfere with air traffic, so those could be a problem. But wind power in the United States doubling about every 2 years. That 3 states, Texas, South Dakota, and North Dakota, they have sufficient wind energy resource exists to satisfy the electricity for the entire country. But the only problem is that it's sort of seasonal. There's a windy season and non-windy season. So during non-windy season, this energy has to be stored. Okay. Okay. Next one is biofuels. Biofuels are like firewood. Biofuel is new name for oldest fuel used by human. Like our old ancestors, they burn wood, get warm to cook food. So those are biofuel. They're firewood, they're charcoal, burning of municipal waste. Only 1% of U.S. municipal waste to recover for energy, 10% can be extracted, 30 to 50% of waste for energy in the Western Europe. Western North American forest was cleared for agricultural, and they burn through the forest. And then firewood is best known as mostly used as biofuels. In some places, people use, in India, for example, or other countries, in Tibet, same thing, they use cattle dung. It's burned for cooking. Peat can be also formed compressed dead vegetations. They can provide heating and cooking fuels. More than 1 billion people in the world today use wood as their primary source of energy for heating and cooking. So these are also going to expand in the future. Okay, so we're almost done. Sorry, it's a long chapter. So in energy business, you see that it's same as all other economic activities. Supply and demand for energy are very difficult, are very important. When the supply is high, then it's going to be cheaper, and demand is high, then it will be more expensive. Same for energy, But these kind of it's something's pretty hard to predict, like the one we talked about, the crisis, the price shock, the $100 per barrel of crude oil or $50. It's sometimes hard to predict. And because either technological, economic, or political and social assumptions and line projections are constantly changing. So it's highly variable and sometimes unpredictable future supply and demand. So we have to minimize energy demand and just energy use. And so there's three things we have to be able to do. They're conservations. So conservation of energy refers to moderation of energy demand, or minimize energy demand. Second thing is efficiency. We have to increase energy efficiency through new technology. The third one is cogeneration. Basically, it's a number of processes that can capture and use some of the waste that heat produced by power generation and industrial operations, rather than simply releasing it into the atmosphere or in water, and where it can cause thermal pollutions. So we use them. These three concepts, conservation, increased efficiency, cogeneration, sometimes can interrelate it. For example, if we produce electricity at large coal-burning power stations, there are also lots of heat maybe emitted into the atmosphere, and we want to reuse them and recycle them. So we have to, if we can increase in energy efficiency, we can cogeneration. So they're sort of related. So energy policy for the future, one role is the development of technology. Involves two paths. One is hard path, which is a continued business as usual. So that's there are two arguments. One is that this is a environment problem due to the use of local resources, industrialization, and technology brings solution to the problem. And this dominant energy planning in the United States, in the past. So this is Europe, because transition is hurting all the infrastructure, for example, if you're changing to cars from burning gasoline into electricity, we have to have changing the car completely, electric cars, for example. So the hard path, business Europe, some people try to be very comfortable and then doing business Europe. And the soft path basically is emphasize energy alternatives, renewable energy, flexible, and they are decentralized, environmentally more benign than those of the hard path. So I think we are slowly turning to the soft path, which so to strategies increase alternative energy sources, transition from oil and coal to other energy resources, and greatly reduce environmental consequences of burning coal and reduce our dependence on foreign oil. And that's the way being decided. So, but this involves using more natural gas, more nuclear power, and other alternative energy sources. So sustainable energy sources, we need to find a new energy path, because the age of cheap oil is coming to an end. And this is reality, whether it's come to this year or 20 years from now. And also technology and economic opportunity are favorable for development use of much more alternative renewable energy. Now, these days, one of the reasons why alternative energy is not able to develop as fully as possible is because the oil is still cheap. So people talk about in the future, when the oil and gas prices increases, then market will decide what kind of technology can be used. And you see that the fracking of shale gas. In 2008, there's a price shock when the oil is $100 per barrel, then the shale gas is popular, and because it's much cheaper than the oil, so it can be exported and so forth. And after the oil price is down, then these days, they're actually more expensive compared to oil. People actually start to drill more wells for tapping shale gas. So we also have to reduce carbon dioxide and air pollutants, so we have to use much less fossil fuels. Energy planning for the future is complicated and necessary to find useful long-term source of energy without causing atmospheric pollution. A transition from hard to soft path environment, continued use of fossil fuel. This is unfortunately, but then we try to avoid coal, but we try to use natural gas, which contains less carbon dioxide compared with coal. And the energy path, which has to satisfy modern society needs without endangering the planet. So these are pretty complicated processes. All right. So there are 4 critical questions for this chapter. I want to answer this question and speculate the possibility of power plants in space. Okay, this is a long chapter. Maybe I explained too much details, but I hope you can enjoy it. And next week, we're going to have midterm exam.